Okay, so welcome back to this RC circuit frequency response after the short break. So, similar to the CR circuit, again here what we are doing is that we are taking the circuit into Laplace domain, namely the impedance of both the elements we are going in Laplace domain. For C, it is 1 by S into C, and this is directly same as this R, and then input it is V in Laplace domain S, and then the corresponding output also we are considering in Laplace domain, which is V O S. And if we analyze this circuit, what we are getting here, it is V O S equals to V in divided by R plus 1 by S C into 1 by S C. So, from that what we are getting is V O S divided by V in S equals to 1 by 1 plus S R C. It is similar to the previous circuit, except of course, we do not have the S R C part, rather in the numerator we do have simply 1. Now, to get the frequency response, as I said for the previous case, what we have to do, we have to take this replace this S by j omega, or rather I was having say sigma part in S, which I am making it 0. So, we are dropping this part, and that gives us the transfer function in Fourier domain, and it becomes 1 by 1 plus j omega R C. Now, this transfer function in Fourier domain, again we can make the gain plot and the phase plot to get the frequency response. So, again here what we can do, we can plot the magnitude. So, if we consider the magnitude of V O j omega divided by V in j omega, and with respect to omega. So, if you see here at low frequency, if we ignore this part with respect to 1, then the corresponding magnitude it is 1. But then if you go to higher and higher frequency, and if this part it is dominating over this 1, then the magnitude wise what we will be seeing here, it is 1 by omega nature. So, I should say it is more like a hyperabolic curve if we consider this part it is dominating. So, beyond some frequency it is going through this hyperabolic nature. So, initially it was approximated like this, and beyond this point it is approximated by this hyperabolic part, and the changeover it is happening again at the same frequency, where omega R C magnitude wise omega R C it becomes equal to 1. So, I should say if I call this is omega 1, at omega 1 what we are getting is that omega 1 R C equals to 1, which means omega 1 equals to 1 divided by R into C. So, if I consider the actual curve instead of considering these two asymptotic or approximated curve, we will be getting the actual curve going like this. So, here again it is having complementary behavior, as I said with respect to the previous one. Before this frequency the circuit it is passing the signal to the output, and that is very obvious from the intuition of this RC circuit, because if the signal frequency it is low enough, then the capacitor it may not be shorting this output signal. As a result, at the output we can get almost this input signal. On the other hand, if you go to higher and higher frequency, this capacitor its impedance it may drop, and then the signal at this output it will be dropping. So, if you consider frequency beyond this omega 1, then you can say that behavior of the circuit it is working like a, the signal is getting attenuated. So, beyond this frequency the signal it is getting attenuated. So, I can say that the circuit it is again it is having two range of frequency, one is pass band and another is the stop band, and in this case it is, we can say, low pass, lower frequency it is getting allowed through this circuit. Now, similar to the previous case, here again we can make the phase plot, and then if you consider the phase plot at very low frequency, this part it is almost 0. So, we do have 0 phase shift. So, you can see that the phase shift here it is 0 degree. So, this y axis is the phase shift offered by this network. So, V o divided by V in j omega, if you consider its phase, then at low frequency it will be 0 degree, and then as we are approaching towards this omega 1, then this part it will be more and more prominent, and then at omega 1 that will be equal to its magnitude wise it will be 1, and so it will be j omega, sorry, this part it will be simply omega. So, the corresponding phase here it will be minus 45 degree, that is because in the denominator at this point I do have 1 plus j, right. And if you go to higher frequency beyond this omega 1, this part it will be dominating, and as a result then we will be going towards minus 90 degree. So, this phase plot and this gain plot, they are giving the total frequency response of this RC circuit. Now, similar to the previous case, again since we like to see the wide range of frequency and the behavior of the frequency response over wide range. So, we need to change this scale into logarithmic form, and magnitude also we like to change in logarithmic form. So, whatever we get is the Bode plot. So, here again in the Bode plot, what we will be seeing, it is similar to the previous case, that if you consider omega in log scale, then of course, 0 frequency it will be pushed to infinite distance, and then this one part it will be coinciding with 0 dB, and then this hyperbolic part on the other hand it will be having a linear behavior, and then at the corner frequency there will be roll off started, and exactly at corner frequency at omega is equal to omega 1 will be having minus 3 dB. Okay. So, again here we can say that this corner frequency, whether it is in, so this is gain or magnitude in dB. So, this corner frequency and whether it is in this frequency response or in Bode plot, it is related to this location of the pole. So, here again we are getting a direct relationship of this pole and this corner frequency. So, just by seeing the transfer function, if we know that the location of the pole, probably from that we can tell what is the location of this corner frequency. And in this case, if we consider lower frequency with respect to this corner frequency, then the gain it is remaining constant, and beyond this point the roll off it is linear, and in fact mathematically it can be shown that or you may be already knowing from other subject that the slope of this gain variation with omega, it is minus 20 dB per decade. So, whenever you are talking about frequency response, in fact what we are looking for is that in some range gain it is remaining constant, and then we are hitting say something called corner frequency, and beyond that it is having a roll off like this minus 20 dB per decade. In case if we consider lower side for the other circuit, then we have seen that beyond some other corner frequency or below of this corner frequency, the slope here it is 20 dB per decade. So, I should say that whenever we are talking about this frequency response, what we are trying to capture, it is the location of the corner frequency, and that can be directly obtained from the pole of the transfer function in Laplace domain. So, so the natural curiosity is that why this pole and this frequency response cutoff frequency, why they are related. So, let us see that part. This part we already have covered, Bode plot we already have covered. So, this is what the we are about to discuss, that the transfer function, pole of transfer function in Laplace domain and the cutoff frequency, they are related. And let us consider this simple RC circuit, which is having one pole, and the location of the pole, it is if you see here, the location of this pole, it is P equals to minus 1 by R c, which means that S is equal to minus 1 by R c, the transfer function, the magnitude here, it will be going to be infinite. So, if I say that this gain or transfer function, if we denote by say A V s, since it is we are dealing with voltage, and if you plot this magnitude as function of S, and S is note that S is having two components. So, one is the sigma part, the real part, and the imaginary part. So, if we plot this magnitude over this S domain. So, this horizontal part, the horizontal part consists of this sigma axis and j omega axis, basically this is the axis. So, we may call this is the S plane, S domain. So, over this domain, S domain, if we plot this magnitude of this transfer function, what we are seeing here, it is since it is having a pole, it is having a pole at this frequency, or say let me consider this one. So, at minus 1 by R c. So, if we sketch this plot, obviously or the surface, if you see, this will be going to infinite at this point. So, if you see this surface, it is more like a tent, and at this frequency the tent, it is going to infinite. So, this is, imagine that this is 3-dimensional plot, and the location of the pole, it is here. So, if you see this surface, and then if you consider the vertical plane constructed by this j omega axis and then this AVS axis, that means this plane consists of this vertical plane, and this plane, it is cutting this surface, whatever the surface just now we are plotting here, which is basically representing the variation of the gain over this S domain. Now, if I consider this cut set of this surface, which is getting cut by this vertical plane constructed by this AV and j omega, what we can see here, it is a cut set having a profile like this. So, the cut here will be seeing a profile like this, and if you see this cut, what is the significance or importance of this one? It is that along this axis, this is also, this axis is also representing some value of s, but along this axis of course, the sigma part equal to 0. So, which means that whenever we are talking about sigma is equal to 0, we are restricting our s domain only along this line. So, if we move along this line, each of these point is representing one frequency component corresponding to whatever the omega we do have. And whatever the surface profile we are seeing here, it is basically representing how much the gain or the attenuation of the input signal it will be experiencing through this circuit. Based on its frequency, this variation it will be obtained. In other words, if I say that in this experiment, if we change this omega frequency starting from say 0 towards higher and higher frequency, and keeping the magnitude input magnitude of the input signal say constant, and if you observe the magnitude of the output signal, what we will be seeing that the with omega how the magnitude it is changing, that profile we can get by this line. So, this line, as I said, this line it is nothing but the response of this circuit for say stimulus whose magnitude is not changing with time. Why magnitude is not changing with time? Because we consider the corresponding stimulus, it is having a sigma is equal to 0. So, whatever the signal we are feeding here, if we consider it is a steady sinusoidal signal, that represents two omega component, one is plus omega and minus omega part, and if you consider this part plus part, then if you see the corresponding variation of the magnitude with the omega, nothing, that is nothing but this line, this curve. And incidentally, this curve it is the frequency response, right. And the interesting thing is that in this case for RC circuit, the value here it is equal to 1, and if you go to a frequency say omega equals to 1 by RC, the corresponding magnitude here you will see it is 1 by root 2. So, if I compare the value of this frequency response at this point and at this point, then where it is 1 by root 2, and if you see that omega is equal to 1 by RC, they are what they are revealing that the location of the pole at 1 by RC, it is having an impression at the frequency response. So, I should say if I draw one say circle centering the origin having a radius of 1 by RC, then that circle it will be cutting this j omega axis at this point. And at this point the magnitude here it is 1 by root 2. So, you may recall that whenever we plot this frequency response of this circuit, we have seen that magnitude it was diminishing with omega. Note that this is in, of course, it is in linear scale, and this is the magnitude, and here it was 1, and at omega 1 which is equal to 1 by RC, the magnitude here it is 1 by root 2. So, this point, the cutoff point or cutoff frequency point, which is basically the image of the location of the pole. In fact, if this location of the pole it is going far away, then the point at which the frequency response it becomes 1 by root 2 of this point, that will also be moving away. So, location of this pole in the Laplace domain and the location of the cutoff frequency, they are related. So, in fact, if you see this circuit, this is of course, a RC circuit. So, based on the location of the pole, we can directly, as I said, that we can find the cutoff frequency, whether it is the frequency response in linear scale or whether it is in Bode plot, the cutoff frequency. In fact, this is also 1 by R c. So, now let us see the, so here we have considered R c circuit, which it was having a pole, and we have seen the relationship to cutoff frequency. Let us look into the other circuit, namely the CR circuit, which is having slightly different transfer function. So, yeah, so this CR circuit, the denominator part it is same, which means that this is also having a pole at s is equal to minus 1 by R c. In addition to that, it is also having a 0, which means that numerator polynomial of this transfer function AVS, it becomes 0 at s is equal to 0, which means that here also it is having a pole, it is having a pole at minus 1 by R c. So, if I am having only one pole, the function supposed to be going to be the surface supposed to be going to be infinite this point. But then unlike the previous case, here it is having a 0, which means that so it is also having a 0 at this point. So, if it is having a 0, then of course, this surface it will be turned down to 0 here. And if you see the impact of this the pole and 0 combination, that gives us a nice surface here. So, this part it is going to infinite, on the other hand this part it is going to be 0. And if you see here, if we travel along this sigma axis, we can see this infinite and 0. But if you consider in other direction, maybe along the j omega also. So, what kind of profile we will be seeing here? It will be going up here, and then it will get saturated like this. So, earlier whatever the cut set we have drawn here along the j omega axis, or rather if I consider this surface, whatever the surface we are trying to explain here, if that surface it is cut by this vertical plane constructed by AV and j omega axis, then whatever the cut set we will be seeing here, it will be having a cut like this. So, whatever the cut set we are getting here, again this is representing the frequency response. And again, depending on the location of this pole, this frequency response, of course, it will be going to steady, and it will be having a corner frequency where the yeah. So, let me use different color here. Yeah. So, we do have a corner frequency where the magnitude of this frequency response, it will be 1 by root 2 times the saturated level. If I turn this curve, and if I see the in this direction, what we can see here, it is this is j omega axis, and this is the sigma axis, which is coming out of the surface. Okay. And this is AB magnitude. What we are trying to explain here, it is having a plot like this. So, this is what the frequency response. In fact, so this line, it is basically the same line here. And again, the location of this pole, it is basically deciding the point where it is going to a point which is having a magnitude which is 1 by root 2 times of this saturated level, and the saturated level, of course, it is 1. So, this point it will be whatever you call 1 by root 2 points, or in Bode plot it is referred as minus 3 dB point, and this frequency again which is omega equals to 1 by RC. So, what is the summary here? We like to say here it is that based on the location of the pole, of this transfer function in Laplace domain, we can directly say that what is the corresponding cutoff frequency. Now, so we have so far discussed about simple circuit, RC circuit and CR circuit, and if we combine this RC circuit and CR circuit together, of course, then whatever the transfer function will be getting, it will be having multiple poles and zeros, those things we will see that. So, let me see the combination of CR and RC circuit, and while you are combining, we need to be careful that loading effect, if we cascade the two circuits, of course, one circuit it may load the other one. To avoid the loading effect, what we have done here, it is we do have the CR circuit, and also we do have the RC circuit, and in between we are putting some ideal kind of block, saying that this block what it is doing is that whatever the voltage it is getting developed called say V1, it produces a voltage here which is a V2, which is equal to constant times this V1. So, I should say that this model, this ideal model of this voltage dependent voltage source, I should say this voltage dependent voltage source ensures that loading effect of this RC circuit is not falling on this CR circuit. So, if the this A naught it is having some magnitude which is higher than 1. So, we can say that this voltage dependent voltage source is an ideal voltage amplifier. So, the whole circuit if you see, you can call it is combination or cascaded of CR circuit followed by amplifier and then followed by RC circuit. And if we stimulate this circuit from this point, and if we like to observe the corresponding output here, what we can see here it is we can get the transfer function of the whole system by considering each of these parts. So, from primary input to primary output transfer function, if we try to see, we can split this transfer function into 3 components. One is coming from this CR circuit, namely V1 divided by V in. So, this is the first part, this is coming from the CR circuit, and then the second part which is coming from the amplifier. So, we do have this amplifier here. So, this part it is basically representing the amplifier. On the other hand, the third part it is the RC circuit, and its transfer function it is basically the VO divided by V2 here. Okay. So, now if we recall that transfer function of this CR circuit, let me use different color here. So, this part it is having a transfer function of S corresponding C and corresponding R divided by 1 plus S corresponding C and R. So, this is the first part, and then the second part is from here to here. So, the corresponding transfer function it is simply this A naught, and then the third part which is RC circuit, and we have seen before that its transfer function it is 1 by S multiplied by the corresponding C and the corresponding R. So, overall the input to output transfer function what we are getting here it is this one, and what you can see here again what we are looking for is the frequency response, and hence the pole of the transfer function, or whatever the factors we do have in the denominator polynomial, one is here, another is here. So, if I consider this factor, it is having a pole called say P 1 equals to 1 by R 1 C 1 with a minus sign. Likewise, if I consider this part, this part we do have the second pole say P 2, which is equal to minus 1 by R 2 into C 2. And this is CR circuit, and we have seen that its frequency response, it is high pass in nature, this is low pass in nature. And for our convenience, let us consider that the high pass frequency, cutoff frequency, it is lower than this one, and then try to see what kind of frequency response intuitively we can get out of that. So, let us so as we have discussed that the transfer function of the whole system, it is given here, and it is having, as I said, it is having two poles, one is coming from here, another it is here, and then also it is having a 0. And if you see the frequency response, let you consider the first one CR circuit, and the CR circuit frequency response, it is so if we plot the omega in log scale and V 1 divided by V in dB, that means if we take 20 log base 10, what we will be getting here, it is basically the high pass behavior. So, we will be getting a frequency response like this. If I consider this is 0 dB level, and then its corner frequency, it is here, which is 1 by R 1 C 1. So, the frequency response of the first part, it is given here. Second part, it is if I consider it is remaining constant. So, I should say that this part, so it is remaining constant, and this level it is 20 log whatever A naught we do have. So, it is remaining constant. On the other hand, the third part, which is RC circuit, it is having it is a low pass kind of behavior, and let me use different color here. For axis, let me use this color, and the body plot of the RC circuit, it is going like this, and then it is having a roll off like this, and the roll off it is happening here, which is say the second pole, let me call this is omega 2, which is equals to 1 by R 2 C 2. Now, if I combine this pink characteristic curve and then the middle one and then the blue one, what we are expecting that it will be just if we overlay the three parts, what we will be getting here, it is so this part, it is coming from the CR circuit and the amplifier. Again, this remains high pass, but then instead of having 0 dB here, I do have some positive gain here, and then if I combine the pink part, then what we will be getting here, it is at some frequency beyond omega 2, it will be having a roll off. So, the overall frequency response, what we are getting here, which is shown here by this red color, which is having a cutoff frequency omega 1 and omega 2. In the middle range, we do have very good gain, which is defined by this one, and this is coming from 1 by R 1 C 1, and this is omega 2, it is coming from 1 by R 2 C 2. So, I think this intuition will be helping you, and of course, this roll off, since it is single pole roll off, later we will discuss about what will happen in case if you have say double pole roll off, namely if you have say two poles exactly at the same frequency, what will happen, but for the time being they are single pole roll off. So, this is minus 20 dB per decade slope, and here we do have the slope, it is positive plus 20 dB per decade, and the middle gain, it is this one. So far whenever we are talking about say CE amplifier or common source amplifier, we were dealing the amplifier in the mid frequency range. To be more precise, we are talking about this frequency range, and then we talked about the voltage gain of CE amplifier and other things. But if you go to lower and lower frequency, depending on the value of this capacitor and then this R, the corresponding gain definitely it will drop. And on the other hand, depending on this R and C, then again beyond some point it will be dropping. So, the actual frequency response or the circuit behavior, it is given by this combined Bode plot, and as I said that it is coming from the 3 elements. So, whenever we will be dealing with actual circuit, it is better to identify which is the RC circuit and which is the CR circuit. They are defining the corresponding the cutoff frequency or corner frequency. So, since our main purpose here it is to use this circuit as an amplifier. So, we can say that this is the suitable range of the amplifier, and if you go beyond this point, then the circuit it is its gain is dropping. So, we are not interested to that. So, likewise if you go beyond this point, then again gain is dropping. So, we are not interested to that. So, we can say that our suitable range it is only this one, and so these two are the limit of the suitable range, or we can say cutoff range or cutoff frequency. One is called lower cutoff frequency, and this one it is called the upper cutoff frequency. So, whenever we will be talking about say amplifier along with the mid frequency range gain, these two informations basically these two frequency cutoff frequencies are also very important to define the frequency response of the amplifier. So, presently whatever the circuit will be dealing with, this model or this CR followed by amplifier followed by RC circuit, this model it is pretty handy and pretty sufficient to explain the behavior of simple frequency response of the simple voltage amplifier. So, we will be talking about this CR circuit common source amplifier and common emitter amplifier circuit. But let me take a short break, and then we will come back to the frequency response of the amplifiers, the actual amplifier.